Hi, this is Nimla Rednam. In this video, we are going to continue the topic mensuration, which is the 9th chapter from NCERT textbook class 8. In the previous videos, we looked at different ways of finding area of a polygon by segmenting it into known areas. And we moved on to three-dimensional solid shapes. And we looked at the surface area of a three-dimensional solid shape by looking at the net of the solid shape. We established the formulae for lateral surface area and total surface area of standard solid shapes like cube, cuboid and cylinder. Now here, if you remember, I mentioned earlier that when you're talking about a two-dimensional, simple closed curve, okay, we are talking about perimeter, which is nothing but the total length of this boundary. Total length of the boundary is nothing but the perimeter, and we look at the area. Area is nothing but whatever is enclosed, the region that is inside this particular boundary is nothing but your area, correct? So this is your area. Now coming to a three-dimensional solid shape, okay. So for example, let me take a cube. I have a three-dimensional solid shape. First thing I look at is the surface area, which is nothing but about the boundary. Now here it's just that for a three-dimensional solid shape, the boundary happens to be this entire sheet that is, enclosing something inside it. And then we look at the volume. What is this volume? It is the space that is existing inside this solid shape. That is nothing but my volume, right? That is the volume of the solid shape. Now here, if you remember, in order to find the area, we tried to fill in the given two-dimensional enclosure with unit squares. So I have a two-dimensional enclosure like this. I'm going to fill it up with unit squares. How many ever squares I require to fill up this entire region, that is going to be my area. Similarly, for volume, what you can do is imagine filling up the volume, the space inside this three-dimensional solid shape using unit cubes, right? If I have unit cubes, how many ever unit cubes it is going to take to fill up the entire volume inside this solid shape, that is going to be the volume of the particular solid shape. That is one way of looking at it. Another way of looking at it is, like they've mentioned here, if you have a stack of newspapers. So here they have mentioned, if you have a stack of newspapers, each newspaper is rectangular in shape and the area is length into breadth, and the stack happens to amount to a height of h, right? So what is this entire volume? Each newspaper area is L into B, right? So you have L into B into h, which is the height. So this is nothing but volume of a cuboid. This is another way of looking at it. So now let us try to establish volume of a cylinder. So for a cube, now that I know volume of a cuboid, cube is going to be a special case of that. For cuboid, it's LBH, right? So the cube, it's going to be a cube, right? And then I'm going to look at cylinder. So how do I find volume of a cylinder? Let us draw a cylinder. When I say cylinder, we are talking about right circular cylinder, correct? So I have right circular cylinder because the axis is perpendicular to the base and the base and the top are circular circles, right? So imagine stacking up circular discs on top of one another until you attain a height of h. Now each disc here is of area pi r square. You already know that area is pi r square. So because the total it's amounting to a height h, The total volume is going to be pi r square h, right? So that is one way of looking at volume of a given solid shape. Now this you can generalize as base area into height for volume, as long as the axis of the solid shape is perpendicular to the base. You can write the volume as base area into height, right? So that is about the volume. Let's look at the examples that they have given. So in the first question, they're asking us take 36 cubes of equal size, right? Let us say they're unit cubes, and in how many ways can you arrange them? They want us to fill in this table. They have given 4 different ways of arranging them in order to get a cuboid, right? So they want us to uh, write the length, breadth and height here. Here the length is 6, breadth is 3, height is 2. And you can see that the volume happens to be 36, right? So in this case, the length is 9, the breadth is 1 and height is 4, and again it is 36. And in the next one, the length is 6, the breadth is 6, the height is 1 and again it is 36. So what do you observe? You can see that when you have fixed number of cubes, you can actually, without even calculation, you can try to understand this concept by saying you have 36 cubes with you and you're arranging them in different ways. Whether it forms a cuboid or not, the volume is neither getting destructed or new volume is not getting added or formed. So the volume is not going to change. It is always going to be 36 cubic units, right? So that is the observation that he wants us to make, right? Now I want you to look at the exhaustive list of all the cuboids that you can form using 36 cubes. So if you remember, we have done this for a different number. I wanted you to write 36 as a product of 3 factors. Okay, all the possible ways of writing 36 as a product of 3 factors is going to give you all the cuboids that you can form using 36 cubes, right? So the logic here, in fact, we have used the logic of volume being constant without realizing it in the previous video. It's because the volume has to be the same. That means the product of length and breadth and height is going to be the same. And so it is going to give us the exhaustive list of all the cuboids that you can form. I want you to list down and look at it. It's more than 4. They have given 4 already. 4 are already given to you in the table that they have mentioned, but more combinations are possible. Now here, this is a very interesting example of actually combinations, permutations and combinations. When you start permutations and combinations, you will see that you will come across many problems that are framed in this fashion, and you will be looking at all the possible exhaustive list of all the possible combinations. But it's interesting to kind of have that concept in your solid shapes and trying to form cuboids using cubes. It's quite interesting. So I would suggest that you do this exercise not only for 36, you can using the net of a cube that I showed you in the previous video, you can use as many cubes as you can, and as a team you can form a group and try to come up with all the possible cuboids, write it in terms of factors, and then also cross verify it with the cubes that you can actually form with the physical cubes that you have at your disposal, right? So I found it very interesting. Also, I've seen that this exhaustive list, depending on the factors, like for example here, you look at the prime factors here, it is 2 into 2 into 3 into 3. You have 2 different prime factors, 2 and 3. Sometimes for the other question in the same chapter, we have 64, okay, where the prime factor is going to be only 2, okay, 2 power 6 is going to give you 64. Now here, in order to find different ways of writing it as a product of three factors, you can actually you can get a glimpse of the concept of partitions. Partitions is nothing but, if you are given a number, how can you write it as all different ways of writing the given number as a sum of positive integers, right? So you get a glimpse of that when you try to partition it, and then you say, for example, this is 4 into 8 into 2, right? So that is another interesting concept. So all I'm requesting you to do is this particular sum, although what the understanding that they want us from this particular question is quite straightforward and simple, and I want you to remember this sum. And when you come across permutations and combinations, when you start, not come across, start those topics, permutations and combinations and partitions, I would like you to remember the small sum that you were introduced to in 8th standard, and that is just nothing but all you were doing there by writing the exhaustive list of combinations was actually permutations and combinations, or the partitions. So that's very interesting. I found it very interesting. And also there is another concept that you have actually introduced here. While finding the volume, you're actually, the stacking up is nothing but integration. So you do have a glimpse of calculus also in this. So many beautiful things without actually mentioning the technical terms, without actually explaining anything about the theory part of it. So many things are introduced. So I would like you to just remember this particular sums of, you know, all the possible ways of forming a cuboid from given number of cubes, and remember how you got volume of a right circular cylinder, and so on. Right. So moving on. Next question is, find the volume of the, this is the next question. Find the volume of the following cuboids. Now this is length into breadth into height. So 8 into 3 into 2, which is nothing but 48 cubic centimeters, or you can write it as centimeter cube also, right? And here they're giving the area. So it's simply area of the base into height, cubic centimeters. That will give you the answer, right? So it is 72 cubic centimeters. Next, they're asking volume of the cube. So 4 cube will be the volume, right? Which is 64 centimeter cube. And here you have 1.5 meters. So 1.5 cube meter cube is going to be the answer. Next question, arrange 64 cubes, this is the one I was talking about, of equal size in as many ways as you can to form a cuboid. Now he's asking the exhaustive list in this case. In 36 cubes he did not ask us, but I want you to find the exhaustive list. But here they're asking you the exhaustive list. Find the surface area of each arrangement. Okay. Now the volume will be the same, but we have seen even in second exercise that surface area is going to be different for each of these cuboids, although the volume is the same. Can solid shapes of same volume have same surface area, right? So they can have different surface areas, right? So let us try to answer the question by writing the exhaustive list of all the cuboids, possible cuboids, and then looking at all the surface areas, right? So 64, I have 64 is nothing but 2 power 6, right? So I'm going to use our original method, one factor. If I have two factors, the first one is going to be 2, and so this will be 32. And if the first one is going to be 4, then it's going to be 16. And if the first one is going to be 8, it's going to be 8, right? And after this, there's going to be a repetition. Now I don't want 1 as the factor, in which case, so yeah, this is the different ways of writing the, all the three factors. Next I have, if I have a 2 here, right, I'm left with 32, right? 32 can be written as 2 into 16, or it can be written as 4 into 8, right? And then that's it. So if I have a 4 here, right, it's going to be 4 into 4 into 4. So you can see that I have 7 different ways of writing 64, of arranging 64 cubes to form a cuboid. Now they're asking us the surface area, right, of each arrangement. So here you know that the surface area of a cuboid is 2 into LV plus BH plus HL. So here it is going to be 1 plus 64 plus 64, right? Let us quickly calculate all the surface areas. So this is 128 and 129 into 2, which will give me 258, right? This is going to be 2 plus 64 plus 32. 98, twice of 98 is 196. This is 4 plus 64 plus 16. 20, 84 into 2 is 168. You can see that the surface area is dropping. 8 plus 64 plus 8, which is 16, 160. This is 4 plus 32 plus 32. 68 is 120. 68 into 2 is 136. And I have 8 plus 32 plus 16, and 56, twice of 56 is 112, and then I have 16 plus 16 plus 16. 16 threes is 48 twos, 96. You can see that the surface area is dropping. You can actually think of a reason why, because as they are increasing, kind of making the dimensions even, you're cancelling off a lot of surface areas of the cubes inside. If you actually do the activity, you will be very clear about why is the surface area coming down. So here, to answer the question, they're asking us how many different ways, right? So you've seen 7 different ways. Okay, so that is the answer, 7 different ways. And can solid shapes of same volume have same surface area? If the question should be, do they have a different surface area? They, with the same volume, okay, same volume, you can have various possibilities for surface areas, many multiple possibilities, okay, for surface areas. So that is the answer for that question, right? And next thing discussion, right? They're saying a company sells biscuits for packing purpose. They're using cuboidal boxes and they've given the dimensions. What size of the box will be economical for the company? When they say economical, that means you don't want to waste a lot of material in packaging. So the material that you use is the surface area is an indication of the material, how much material you have used for packaging, right? So clearly you have seen here that depending on the arrangement of the cubes, you will have different surface areas. Okay, the surface area is dropping, okay, when you are trying to use different dimensions. So what you're going to do for economical purposes is you're going to use the minimum surface area. So here they have given 2 possibilities. So of these 2 possibilities, which one gives you lesser surface area is going to give you more economical, it's going to be more economical for the company. Why? We have just discussed it. So is there any other size which has the same volume but more economical than these? First, let's look at the volume to understand what is this. So you have 3 into 8 into 20, 3 into 8 into 20 is going to be 480, right? Centimeter cube. This is the volume that we are talking about. So if you look at the surface area, in the case of A, let us solve this sum. In the case of A, where the dimensions are 3 by 8 by 20, 3 by 8 by 20, the surface area is going to be 2 times of 24 plus 160 plus 60, right, which is nothing but 244, 488. This is going to be the surface area, correct? So that is the surface area. For the box B, the dimensions are 4 by 12 by 10. Okay, so for B it is 4 by 12 by 10. So the surface area is 48 plus 120 plus 40, right? This is nothing but 160 and 208. So I have 416 square centimeters. So that is my surface area. So clearly box B is going to be more economical because it has lesser surface area compared to box A. Now they are asking, in the question they are mentioning, is there any other box which is even more economical than these two? Okay, so in order to answer this question, you need to list down all the possible arrangements of this of the factors of 480 and try to write 480 as a factor of as a product of three factors and see which one gives you the least surface area, right? So that is how we are going to proceed. So that exhaustive list is going to take quite some time, but I will let us discuss an approach at least. So here, if I have, right, I'm talking about the volume is 480, correct? We have seen that the total volume is going to be 480, right? Let's look at the factors here first. Okay, so like I said, I want the exhaustive list and you'll start with 1 into 1 into 480 and you'll go on, right? You're going to get a long list. What I am suggesting is, if you remember, if you look at the previous calculation that we have done, the surface area is dropping, right, when I'm trying to get numbers close to each other as the factors. Now here you can see that 1 into 1 into 64, there's a lot of difference between 1 and 64. The gap is very high. Or if you want to look at it in terms of the activity that we have done, when you have 1 by 1 by 64, you're stacking them in a line. Only, one or maximum two sides are getting cancelled. Surface areas, two sides are getting cancelled for each cube, one or two, not more than that. But when you try to, arrange them in such a manner that the dimensions are closer to each other, then you will end up with a smaller or a lesser surface area, right? You can see that it's dropping. It is consistently dropping until you have a cube which gives you the least, right? So keeping this in mind, let me first do the prime factorization of 480, right? If I do the prime factorization of 480, I am going to have 30, 15, which is 3 into 5. So 480 is nothing but 2 5s, 1 3 and 1 5. Sorry, 5 2s, 5 2s, 5 2s, 1 3 and 1 5, right? So I'm going to fill up 3 baskets, right? And I want these 3 baskets, the numbers in these 3 baskets to be as close to each other as possible, right? So let me put 3, 2, 3, 5, and because 2 is very less, I'll put another. So this is over, and another 2 over here I'm going to put. Now this becomes 4, this is 3, and this is 5, very close. So one way is to put each 2 in one of these baskets. Let us do that. That's the first possibility. Let me look at that. So I'll end up with 8, 6 and 10. Correct? Or let us try to put, this is the least one. So what if I put 2 2s in this basket? It becomes 12, right? And 12 is really far off from 4 and 5. Even if I add the remaining 2 here, it becomes 8. And still this is really far off from these two. So you can see that 6, 8, 10 seems to be, you can check the exhaustive lift and check and let me know if it is the right answer or not. This seems to be the closest, the factors seem to be closest to one another. And in this case, let us see the surface area, how different it is from the ones that we calculated. I have 48, 60 and 80. So this is 188 into 2, right? So this gives me in the previous 188 into 2, right? So this is going to give me 276, whereas in the previous case I got the surface area in 400s centimeters square. So you can see that the surface area has reduced drastically, and this will definitely be more economical for the company for packaging purposes. So this answers our question of think, discuss and write, right? So going forward, we have already discussed the volume of a cylinder. They've asked some simple questions on these two cylinders. Pi r square into this will give you the volume, and over here it is 250 is already given to you. So into 2 if you do, you're going to get the volume of the, this is centimeter cube, this is meter cube, volume of the given cylinder. So you can look at volume of a cylinder as pi r square h, or base of the circle, base of the area of the base into height. Next comes volume and capacity. Now here capacity. Here capacity is a term usually used for liquids. That is, if you have a container, you usually say what is the capacity of the container. That is how many liters of a given liquid can you fill in this particular container. Also capacity in colloquial sense, it is used for, you know, what is the capacity of a room. That is number of chairs that you can fit in for a particular, you know, in a room so as to conduct a class or a show or anything. Now here you have a relation between the you know, centimeter cube and the ml, which is capacity units are milliliters, and 1 milliliter is equal to 1 centimeter cube. That is, if you have a cube of 1 centimeter cube volume, that is, if you have a unit cube, the liquid that you fill in that unit cube is going to be 1 ml, right? So that is the relation between the units liters and the meter cube, right? So from this, if you remember this, all the rest will follow from there, right? So they have given a few solved examples where again, like we discussed, base area into height. If you remember this, you will be able to solve these questions. So you have a cuboid here, and how many you know, cubes can you fill in that? This will help you in visualizing volume of a given solid shape in terms of filling it up with unit cubes, right? And then this is using this net. You know that net of a cylinder is actually a rectangle if you're looking only at the lateral surface. That is, the cylinder is open at the bottom and at the top. Then you can calculate the volume from that. If you find R, you can calculate the volume. So that is about the solved examples. Here again, they've looked at a rectangular piece of paper, and you know how to arrive at a cylinder from a rectangular piece of paper. So with this, we come to the end of discussing all these solved examples for this particular exercise. In the next video, I'm going to discuss at length these 4 solved examples and then the sums of exercise 9.3. And with that, we are going to finish this topic mensuration.